Hello everybody, how are you? Today we are going to explain memory organization with cache memory. Okay, actually in a computer system, usually it's not constructed using a sort of single type of memory at all. In fact, in here several types of memory are used actually. That actually comprise the hierarchical memory system of the computer. In a typical hierarchical memory system, the most well-known element of the memory subsystem is the physical memory or DRAM type memory. Okay, when a company, actually a computer manufacturer, advertises a personal computer for sale with suppose 128 MB or some sort of other thing of RAM, they are actually referring the physical memory. Okay. As processor speeds increases, the physical memory becomes a bottleneck in system performance, right? A fast microprocessor may have a clock frequency of over suppose 500 MHz, resulting it in a clock period of less than 2 nanoseconds. Fast DRAM has access time of about 30 times that value. A computer system with only physical memory, I repeat, would spend most of its time waiting for data. This is the motivation to use of cache memory. Okay. Cache memory are constructed with static RAM type chips. It is much more faster than DRAM cells, with access time on the order of about 10 nanoseconds. It is also much more expensive than the DRAM used to construct the physical memory, which is why computers usually are not built using only SRAM. Okay. In the memory hierarchy, cache memory is situated just closer to the microprocessor. Actually, I have already circled it with the red. Actually, main memory is there too, and CPU is there too, and cache memory is just situated between them in a red circle over there. Okay. Cache memory itself can be arranged hierarchically, right? Usually with two levels. The first level is called the level 1 cache, or somewhere it's called L1 cache, which is incorporated directly into the microprocessor, right? There are several options for external level 2 cache in some architectures. Where it's called L2 cache. Okay, it is usually situated just outside of the microprocessor. Okay, actually a cache controller copies data from physical memory to cache memory before or when the CPU needs it, right? Associative memory are used to construct a cache type memory with associative mapping, or an associative cache. Consider the relatively simple CPU organization that can access 64K of 8-bit memory. An associative cache for this system could be constructed from associative memory that has 24 bits wider. Right. Although the associative memory required for the regular configuration is much wider than the usual requirement, it offers a significant benefit. It takes the advantage of locality of reference. The concept locality of reference actually constructed with two different portions. One is called temporal locality, another one is called spatial locality. In temporal locality, information is actually reuses like a loop. And in spatial locality, actually it works as a array type memory. Related data items are usually stored together in a consecutive memory location. Instructions are executed sequentially in spatial locality, where in temporal locality the information are reuses like a loop. Actually, when an instruction at memory location, suppose XYZ, is accessed, it is very likely that the next instruction to be executed will be the instruction at location XYZ plus 1. assume that for associative memory with and without data blocks, the CPU must execute the instruction at first location, that is location 0 actually, which is not in the cache. In the configuration without blocks, the instruction is read from the physical memory and then copied into the cache. After this, instruction has been executed, the CPU requests the instruction at location 1, actually 0 plus 1, location 0 plus 1, which also is not in the cache. That instruction is also fetched from physical memory and then copied into the cache. The same thing happens for the instruction at consecutive position like second and third or somewhere else, right? Actually, in location 1, 2 and 3, what I have already told, they are already in the cache and can be fetched from there rather than from the slower physical memory. For this common pattern of instruction access, the cache with data blocks significantly outperforms the cache with single data value. Let's have some brief idea on performance measuring of a cache type memory. The primary reason for including cache memory in a computer was to improve system performance by reducing the time needed to access the memory. But claiming to improve performance isn't enough actually, you know. We must verify and sort of quantify this improvement. The primary component of cache performance are cache hits and cache miss. Every time the CPU accesses the memory, it checks the cache first. If the requested data is in cache, the CPU accesses the data in the cache rather than physical memory. This is called cache hit. If the data is not present in the cache, in that case the CPU has to access the data from the main memory. In that case, usually it writes the same data into the cache as well. This is called a cache miss. The hit ratio is the percentage of memory accesses that are served from the cache rather than from physical memory. The higher hit ratio in a architecture, it means the more times the CPU accesses the relatively fast cache memory and the better the system performance. The hit ratio can be determined via system simulation or sometimes by physical monitoring of the computer system hardware while it executes code. Hit ratio of over 90% must be achieved under favorable condition. The average memory access time, or TM, T suffix M actually, okay, is the weighted average of the cache access time. TC plus TC actually average access time for the cache, you know, plus the access time for physical memory called TP. The weighting factor is the hit ratio or H, small h actually, okay. So TM or average access time may be calculated as TM equals to H cross TC plus 1 minus H into TM. Since TC is mass length less than the TP actually, it increasing the hit ratio reduces the average memory access time. Okay, here we have a example where TC equals to 0.4 microsecond, TM equals to 1.2 microsecond, and heat is 85%, and that actually results 0.58 microsecond of TC. Okay, that's all for that particular video. The next video will be available soon on cache. Thank you. Keep watching.